my name is Belinda Paterno, and we're here today at Crystal Springs at Titlow Park. I'm part of the Stream Team program, part of the Conservation District, and we are here to demonstrate our flow or our discharge measurement for Stream Team. And that is just calculating how much water is coming down a stream at like a single kind of point in time. And so we're going to demonstrate that and what the equipment that you need. It's really helpful if you're wearing boots or some shoes that you don't mind getting wet. So it's a little bit easier to get into the stream to do this kind of measurement. We also don't do this measurement when we know there's salmon spawning times. So we typically only do the float or discharge, or the flow or discharge measurement during the summer months when we know that there's no salmon reds or salmon that are spawning. And since we do have to get into the creek and disturb it a little bit. So the equipment that you'll need besides boots or waterproof shoes is a tape measure to measure the width. You'll also need a depth stick, which is measured in tenths of feet for our depth. And these are all things that we are providing you as a Stream Team monitor. And then our last items that you'll need are something that will float to do our timed float. And so we provide two balls that are light enough that they float on the surface. You can also use a leaf or a twig or something else nearby on your stream that can act as a float. So our first part for doing the discharge measurement is measuring out a stream length of 20 feet. If you're unable to measure 20 feet because of a meander or if the stream banks are inaccessible, feel free to go down to 10 or another length that's easier to measure. For us here at Crystal Springs, we're able to measure out to 20 feet. So Aru is going to walk backwards to 20 feet to measure. And I am going to make a mark where my 0 feet is, and Aru's going to walk to 20 feet. And we're making marks so that way we can use our tape measure in the future and just remember where our 20 feet is. So our next step for doing the discharge measurement is measuring the width of our upstream transect. And we're doing the wetted width where the water is flowing in the stream. And we're going to measure it in feet across. And we're starting with that upstream transect mark that we already made. And so Aru's going to hold their end near the edge of the wetted width over there. And then I will measure in feet where the wetted width is here. And we have 5.5 feet across for our wetted width, and so that's what I will record on our data sheet for the upstream transect. So our next step for doing the discharge calculation or measurement is doing our depth measurements across the width of our stream at our upstream transect. So I have my mark on the side here and kind of like an invisible line going across. You're welcome to leave the tape measure across too to give you more of a visual representation of that line. Just make sure you're going in a straight line across. The goal is to get 7 depth measurements. It's really 8 altogether, but 0 is already filled in kind of as your shoreline. And so this is, the depth stick is measured in tenths of feet. If you have a really high flow coming downstream, sometimes the water will be higher on the upstream side and then lower on the downstream side. So you kind of want to take the average if that is the case. So I like to just kind of visually represent kind of what 7 measurements are across. You don't have to be super specific and get equal distance between those 7, just as long as they're kind of the average across. So our first measurement is 0.1. I'm going to record that on our data sheet. Our second is another 0.1. Our third, 0.15. Our fourth is another 0.15. Our fifth is right at 0.2. Our sixth is 0.2. And then our seventh is 0.15. So once we have our 8 depth measurements, we're going to take the average of those 8, so we're going to add those total 8 all together, divide by 8 to get our average depth. We're then going to take our width that we already measured for our upstream, which was 5.5 feet, times our average depth, and that will give us feet squared for our upstream transect. So our next step for doing the discharge calculation is doing the downstream transect. So we're going to take the width across. Again, it's a wetted width for our downstream transect. So I'm going to move across the stream here. Aru is going to bring their end of the tape measure to the edge of the stream. So I am measuring for our wetted width is 6.6 feet across. And that's what I'll record on my data sheet for the downstream transect width. So for our downstream transect, we're going to do our depth measurements across again. We're going to record 7, but remember it's 8 all together. So for our first measurement, we have 0.2. I'm going to record that on my data sheet. And this will be shown at the end, the data sheet, that way you get an up-close view of it. My second depth measurement is 0.2. My third is 0.25. My fourth is 0.3. My fifth is 0.3. My sixth is 0.4. My last measurement is 0.2. So now that I have my depth measurements for our downstream transect, we're going to take the average of those again. So we're going to add up all 8 measurements, divide by 8 to get an average depth. To understand our average depth in feet squared, we're going to take our width, which we already calculated at 6.6 feet, times our average depth, and that will give us feet squared. Again, at the very end, we'll show this data sheet so you can see it up close with the calculations. Once I have my average depth in feet squared for both the upstream and the downstream transect, we're going to take the average of those two. So we're going to add those two up, divide by 2, to give us our average cross-sectional area in feet squared. So working down our discharge calculation sheet, we've already filled in our average cross-sectional area. We already have our length of our stream reach filled in at 20 feet. Our next box that we need to fill in is our correction factor for the stream bottom. Depending on if you have cobble or a muddy bottom stream, it's going to give you different friction for what the water is, for the water velocity, so you need to calculate that in as part of your discharge calculation. This data sheet was based on a discharge calculation developed by the EPA, and they determined that a correction factor for a rocky bottom or a cobble stream is 0.8. A correction factor for a muddy bottom is 0.9. So you're going to look at your stream bottom and figure out what is the predominant stream bed that you see. For here at Crystal Springs, even though we have a lot of sediment here where we're measuring, we still have a lot of cobble or rock present underneath that sediment. So for this stream, I am going to classify it as a rocky bottom stream. So that's what I will fill out on my data sheet. I'll do 0.8 for a rocky bottom for my correction factor. So our next and kind of one of our last steps to do with our discharge calculation is actually to do our float calculation to see how long it takes for an item to float down the stream as part of our total discharge. And so we have our upstream transect and our downstream transect. It's really helpful to have two people involved with this. If you were by yourself, you could always use a leaf or something that you find near your stream as a float. That way you don't have to worry about catching a ball downstream. I like to stand just upstream of my mark for the transect, and then at the downstream end, that person would stand just a little bit farther back from that downstream end of that mark. That way they can see when it crosses the line. So I will drop my ball a little bit upstream, and I will start my watch, and then Aru at the end is going to catch the ball and yell out stop. That way I have my time for this first float, and we're going to do 3 all together and take the average. So I'm going to drop my ball upstream of our upstream transect here, and then start my timer.
Stop.
Alright, I stopped my watch. I have 24.95 seconds, and that's what I'll record for our first trial, and we're going to do 3 all together. Alright, we're going to do our second time trial, so I'm going to drop the ball just upstream of that transect.
Stop.
Our second time trial was 20.73 seconds, and that's what I'll record on my data sheet. Okay. So our last, we're going to do our third and final time trial, so I'm going to drop the ball just upstream, press start on the timer.
Stop.
So for our last time trial, that's a little bit longer. We got a little bit slower part of the stream, but that's why we take an average. That was 48.96 seconds. And what we're going to do is then take the average of those time trials. So we're going to add them up and divide by 3 and get our average time in seconds. So now I have all my recorded measurements I need for my discharge calculation, which is at the very bottom of our data sheet here. C multiplied together divided by time. So our A is our average cross-sectional area, which we figured out in this rectangle box, times our length, our L, of 20 feet, times our C, which is our correction factor of 0.8 for a rocky bottom stream. And then we're going to divide that by time, which was our average time trials that we just took. And that'll give us cubic feet per second. And again, at the end, you'll be able to see this completed data sheet.
Okay, so this is the stream discharge calculation sheet, and I'm going to go through it step by step and give a little explanation with everything. So the first thing here, you have your stream name, which you should put there alongside the site number, which you should get the first time you monitor at a new site. Going through the equation itself, we have discharge equals A times L times C all over T. An explanation for each of those variables is that A is equal to the cross-sectional area of the stream, L is equal to the length of the stream reach measured, usually 20 feet or so. Sometimes can be shorter than that if you can't reach parts of your stream. C is equal to the correction factor, 0.8 for rocky bottom or 0.9 for muddy bottom. And T is equal to time in seconds for the ball to travel the length of your stream reach measured. So this is broken up into multiple parts, but we're going to start by solving the average cross-sectional area, or A, which is back here in that discharge formula. So Belinda has already written down the stream width for Transect 1, which is the upstream transect, and written down the 7 measurements, and there is a 8th here, but it's just 0, so technically there's 8 measurements, but you only actually measure 7 total. And so first thing I'm going to do is I'm going to bring out my calculator here. So I'm going to add each one of those measurements up. So we'll add 7 total, so 0.1 plus 0.1 plus 0.15 plus 0.15 plus 0.2 plus 0.15. And then you don't have to do plus 0, but if you want to do it just for your memory's sake, so plus 0. And that's going to be equal to 0.85. So I'm going to write that here in the total section, 0.85. And then because we have technically 8 measurements here, we're going to divide it by 8 to get that average. So we divide that by 8 and we get 0.106. And then we do the same with the second transect, which is the downstream. So same idea, we have our 7 different measurements plus that 0. So I'm going to add those all together here. 0.2 plus 0.2 plus 0.25 plus 0.3 plus 0.3 plus 0.4 plus 0.2, and that is equal to 1.85. And divide that by 8, we get 0.231. So now that we have both the average depths of our transects, we're going to go to the cross-sectional area and go and find each of the cross-sectional areas for each of the transects. So, cross-sectional area of transect number 1 is equal to total width in feet times the average depth in feet. So our total width here is 5.5, and our average depth, which we just found, is 0.106. Now, bringing the calculator out here, 5.5 feet times 0.106 feet is equal to 0.583 feet squared. So now we're going to do the same thing that we did with this transect number 1 over here. So cross-sectional area of transect number 2, again, is equal to total width in this case 6.6, and multiply that by the average depth, in this case, which we just found, 0.231. So now, add that into our calculator here. 6.6 times 0.231, 1.52. Now that we have both cross-sectional areas for Transect 1 and Transect 2, all we have to do here is a simple average. So we'll start by writing down our Transect 1 right here. I'm just going to label that T1, and I'm going to put T2 here, just for memory's sake. So we have 0.583 for this first one here, 0.583, and then we have 1.52 for this second one here. And then we just add them together, order of operations and all that. So we have 0.583 plus 1.52. That gives us 2.10. Divide that by 2, and we get 1.05 feet squared. So if you haven't already, the next step is to add in your stream reach, which is typically 20 feet, sometimes 10 if it's hard to get to the different areas of the stream you're monitoring. And then you need to choose your correction factor. In this case, we had a rocky bed, so I'm going to put 0.8 for our correction factor. And before we put those into the final equation, we need to find our average travel time. So we did 3 different trials. First one was 24.95, second was 20.73, and the third was 48.96. So we're going to add all those up, get the handy dandy calculator out here. So we have 24.95 plus 20.73 plus 48.96. And that total is 94.64. Now, since we're doing an average, we have 3 different trials, so we divide it by 3. And that gives us an average of 31.5 seconds. Now, we're going to find our discharge by combining all of the stuff we solved for down in this long equation here. Trust me, it's a lot easier than it looks. So, I'm going to mark these off first. We have ALC divided by T. So this one is our A, this one's our L, this one's our C, and this one's our T. And these all correspond with the stuff up here that we found. So our A is our average cross-sectional area, which we found as 1.05. Our L is the length of our stream reach, which is 20 feet. And then for our correction factor, which we have already chosen based on the location, is 0.8. And our time, which we just found, 31.5. So, to do this correctly, we got to remember our order of operations. So we do the stuff in the parentheses first. So we have 1.05 times 20 times 0.8, and that is equal to 16.8. So I'm just going to say that's all equal to 16.8, and then we're going to divide that by our time, 31.5, and that equals 0.53 cubic feet per second. And that right there is your final answer and should complete your stream discharge calculation sheet.